Game time. All right. Welcome, everyone. My name is Brian. I'm an academic staff member with the University of Wisconsin-Madison. I've been part of the broader UW system for the last 15 years. Done stuff from water quality, soil health, anaerobic digestion. Today, I'm going to talk about a project that our broader team has been working on at Madison for the last couple of years. Um, but Cyanobacteria is a biofertilizer production from dairy manure. Quick here, I think this group is very well versed on understanding phosphorus and most of the phosphorus used in fertilizers is not a renewable source. We heard this morning about linear economy and more circular. We can use things like manure. We know with different challenges from our environment that phosphorus can mitigate or migrate very easily on that. We first the nitrogen ratio, it very easily can be over um, your waterways and cause. So look at an alternative potential nutrient management strategy. Fertile circle to the process. Bacteria, blue-green algae, even though it's not an algae, it's a photosynthetic organism, autotrophic bacteria, and again, it can sequester nutrients, can you produce its own energy, and a great thing about it as well is that it can have a nitrogen phosphorus balance that can be much lower than traditional manure, and we'll get into some of those examples. Just very briefly, this is a much bigger project with a multifunctional team across many different departments, many faculty. I'm just one member here today presenting, but there's a lot of great work by a lot of other individuals that have gone into this. And I'll be covering different aspects of that, whether it be the genetic engineering people, the modelers, the field scientists. So again, variety of faculty, staff, and students. Our proposed system here, as we kind of start the process and look at, okay, what are we going to model? What are we going to do? What are we going to try to develop and improve? It's really taking manure waste streams again, putting it through anaerobic digestion first to capture some of those greenhouse gas and reduce some of those emissions, make methane, make CO2, take some of that CO2, put it through photobioreactors to create that cyanobacteria, feed into them this separated digestate slurry from the digester, so they can then sequester and absorb that phosphorus, put it through dewatering, and ultimately have a dried product that can be used as the alternative fertilizer source. But how do we get to there? So it seems great, but that's very complex system, lots of costs involved. To make this, how can we do this to make this actually fully dairy system? So first, if we start with lots of different modeling, technical economic analysis, analysis, what levers can we pull and play to drive down the cost and scale to make it supportable on farm. Again, genetic engineering to really optimize that organism. We heard this morning's open talk, something I wasn't aware of, and on the tour yesterday, being in Idaho, like I didn't know we could have vegan trout and that they could assimilate more phosphorus. Phosphorus is a nutrient management tool. Here we're looking at study to see if it can be a suitable replacement for fertilizer for crop needs. As we get in the analysis, I wanted to focus on coverage charge, cost of land and water, and how can we be different that we biggest drop to really do efficiency and 25% variable that you're looking at. If intensity, a certain ratio, we found that the biggest driver to really reduce costs and that we wanted to then focus on initially was phosphorus density of the cyanobacteria. To do this, the genetic engineering group and team used our wild type cyanobacterial. They then wanted to do, standard genetic engineering practices to really increase that phosphorus density of the organism, and really focused on phosphorus uptake and phosphorus storage of that. Looking at different genes that are expressed and targeting those. They could then grow batches of this cyanobacteria in the laboratory, harvest that, and through analysis, looking at, again, how much can we increase that optical density of the thing? Is it absorbing that phosphorus? Can we look at, phosphorus loading and really optimize that over repeated trials? Um, Again, a lot of work here that went done over a couple of years to do this. But again, when we really look at, what kind of results do we get through this engineering, we can see in the wild type, around 1.5% phosphorus by weight, compared to the or the genetically engineered cyanobacteria. We're at 8.5-fold increase in that phosphorus loading where we're at today. Some additional benefits we were able to get, higher potassium, reduced carbon density, and really decreasing that phosphorus nitrogen to phosphorus ratio. So then it can be the state that's more readily able to be manipulated with the farmer to not over apply that phosphorus. Um, as we're working with the wild strains, we want to see can they be a suitable product to use to grow crops. We started with greenhouse trials. Again, using a cyanobacteria biofertilizer, dry product, wild type and genetic modified strains. We decided to use oats as our plant of choice that relatively quick growth time. We'll reduce space in our greenhouse due to space constraints we had at our site, and we could implement these pretty quickly. Looking at biomass and different properties in the soil and in the plant matter. Wild type by weight, we look at a block design, looking at the cyanobacteria versus dairy manure, versus synthetic fertilizer, and all that. Really targeting rates 30, 40, and 50. Again, we were able to harvest, usually you could see, we have dairy, we have the triple phosphate, and then we have the and again, looking at a action at a kilogram per hectare, the dairy and the triple phosphate. Additionally, with plant matter, I'll look at phosphate taken in the plants. And again, we were able to find in this initial study, cyanobacteria performed as well or better than the other fertilizer products. Repeated the study, same basic study using that genetic mutant. This one was just completed more recently, but same study design, same exact thing, just that higher, 10% loaded phosphorus product. Thus far, all we have right now is above the biomass data. All the other analytical soil and plant data is still waiting to come back from the laboratory. But again, we're finding, similar capabilities with that compared to other standard things. Based on all the additional learnings thus far, again, we feed that information back into our modeling systems to really drive down, and simplify the process of this using simplified bag photobioreactors. As we dive into the techno-economic analysis a little bit more, we can, again, update our modeling systems through a modeling team and really see that, we're basically looking at, the wild type versus the mutant strain, and really see how we can really drive down the space needs, the cost, water use, phosphorus recovery charges, 50% reduction, and really drive down those costs and size and scale the system. If you look at the total annual costs of this through our modeling, again, we're able to drive that cost in half already right now. If you look at this a little further, here's just the cost of the anaerobic digestion system and the drying system. So that's making up a huge percentage of our total cost of that system still now. So part of the direction the team's starting to lean towards now is maybe, should we have that as part of our system, or should we maybe even remove that to further drop down the cost so it can be comparable? It's down lower, so it can actually be implemented at the site. Thus far, the current system models and strain that's been developed, we're get that down to about about a penny and a half per gallon for treating wastewater. Uh, a lot of work. Again, there's hopeful papers on this, but again, looking at the greenhouse gas emissions reductions using the pathway and biofertilizer. Uh, um, liquid separation here. We have anaerobic digestion. So really looking at, how does the cyanobacteria compare? Uh, uh, some of that complex mesh diagram. Element of the A, we're able to drive ideal, nitrogen. Similar with ammonium, the cyanobacteria. Here, if we can get to that ideal mutant strain, some of our next steps, we can drive that down even further. Summary so far to date of what we've accomplished, technical economic analysis highlighted that, again, we can really focus on that phosphorus density as our key driving to really improve the system and viability of using this organism. Again, we were able to get 8.5 times increase in density of phosphorus loading compared to wild type. Can be used as effective growth media as a phosphorus supplement source, reduce strains, and really driving down, what are the driving main factors that can drive down that cost. Additional work that's coming up this year now, we're actually moving into field trial season. Joe mentioned, some of the other fields that they're going to be applying with Tyler. Tyler and I are working, and Juma and some other people on the team here. We'll be actually doing full field trials, adding cyanobacteria out at our Arlington research site coming up in the next couple weeks. Again, additional engineering is taking place by the engineering team to really make that ideal mutant that can also do phosphorus and nitrogen. And again, doing other data and things that we can put into our models and continually drive down and optimize the system design. One field trial that will be starting again in the next 2 weeks. These are 30 by, I think, 100-foot plots. Again, really just looking at this will be using wild type algae at this point in time. And looking at, again, how can we use that as a fertilizer supplement for phosphorus? And then we'll be taking soil sampling, emissions data in the field, plant data, harvest data, nitrogen use efficiency studies, and gathering all the data. So that'll be great this summer. Another project that helps align working with private industry with Grossman Technologies. They're a company that has a patented this vertical rotating belt system that they can thin film, and they use wastewater applications today where they're making pelletized products they sell. But one of the big constraints is of drying and pelletizing this product. So we're actually going to be doing a study with them out again at our Arlington field station. I think 350-foot plots, where we're really going to be using biostimulant as a soil amendment to look at, again, as a wet product. So if we find data that support that this is a good biostimulant, they might be able to skip some drying steps. Acceptable.